Lesson 4. Gradient, Energy. Section 4.2. Gradient. If E along L is known, then we can obtain the voltage V using this equation. This equation is used to find V from E. For this derivation of V, we need to know E from the start point to the end point of the integral path L. In reverse, if V is known, and E is not, then how can we find E? This is the answer to the question. This operator is called del. If it is applied to a scalar function V, it is called the gradient of V. It can also be written in this form. This is the definition of the gradient of V. It is a vector differential operator. This is to obtain E from V. For this derivation of E, we only need local information about V. Let's see an example how to calculate a gradient of V. A point P is r meters away from the origin of Cartesian coordinates, where a point charge positive q coulombs is placed. In section 3.2, the potential V at P was given by this equation. The distance r is expressed by this equation, where x, y, and z are the coordinates of P. Then the partial derivative of V with respect to x is derived as shown in this equation. The process of partial differentiation is shown in this equation. Pause the video and check the process. The partial derivatives with respect to y and z are also derived as shown in these equations. Thus, E at point P, which is negative gradient of V, is obtained as shown in this equation. Pause the video, and follow the derivation process. Now let's see the meaning of gradient of V. These are cross-sectional lines of equipotential surfaces. One has the potential V, and the other has V plus dV, where dV is a differential potential. The electric field intensity E on the equipotential surface is normal to the surface. If a differential displacement dl is like this one, then the differential potential dV is given by this equation. For simplicity, let's suppose that E and dl are in the xy plane. dl is decomposed into the x element dx, and the y element dy. The differential voltage dV is given by the partial derivative of V with respect to x, multiplied by the differential displacement dx, plus the partial derivative of V with respect to y, multiplied by the differential displacement dy. Ax and ay are unit vectors along the x-axis and y-axis respectively. The inner products of Ax and Ay are given by these equations. Using these relationships of unit vectors, dV is factorized into the form of an inner product as shown in this equation. The first term is, by definition, the gradient of V. The second term is dl. In conclusion, the relationship E equals negative gradient of V is derived. This is the extended form in 3D space. Exercise 4.2.1. Pause the video and solve the problem. Find the electric field intensity E at the point where r is greater than or equal to the radius a, and at the point where r is less than or equal to a. This is the answer to exercise 4.2.1. This is the case where R is longer than or equal to A. Pause the video, and check the answer. This is the case where R is less than or equal to A. Pause the video, and check the answer. Exercise 4.2.2. This is your homework. Pause the video, and answer the problem. Find the electric field intensity E at P. Exercise 4.2.3. This is your homework. Pause the video, and answer the problem. Find the electric field intensity E1 and E2 at P1 and P2. Exercise 4.2.4. This is your homework. Pause the video, and answer the problem. Find the electric field intensity E at P. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.